Hi everyone. In the previous unit, Unit 6, we learned how to synthesize alkyl halides via radical reactions. In this unit, Unit 7, we're going to take those alkyl halides and continue the synthesis and do what's called substitution reactions. This cartoon actually shows that there are two ways to do a substitution reaction. In the first row, it seems like we're substituting the gray cat for the striped orange cat, but in this situation the gray cat leaves on its own and then the striped orange cat takes its place. But look at the second row. In the second row we have a very aggressive orange cat, and that atom or molecule is forcing out the gray cat. We could call the gray cat the leaving group. The thing is, whether you do this process like the first row or the second row, you notice that the starting materials are identical and also the final products are identical. Okay. Let me review that alkyl halide synthesis reaction that we learned in Unit 6, and then we'll carry it on for these substitution reactions. So in Unit 6, we could take this alkane, and to do a radical halogenation, we're going to use Br2 and light. Okay. The abbreviation for light is Planck's constant times the frequency. That's actually the energy of a photon of light. And the product is put the bromine on the secondary carbon. Okay. And it doesn't matter which carbon you use, the secondary carbon here or over here. It will be the same product. We're disregarding stereochemistry. We know that the bromine can come from the front or the back, giving a 50-50 mixture, but at this point we're not concerned about that. In Unit 7, we could take the starting material and do what's called a substitution reaction. Technically, this reaction up here is substitution because we took off a hydrogen and we replaced it with a bromine atom, but it's not. We mostly consider this a radical reaction. The substitution reactions are not radical reactions. They actually move in the mechanism 2 electrons at a time. So we're back to our normal mechanism arrow, where we're using full arrows and not fishhook arrows like we did in radicals. Let me just write this radical halogenation. Okay, so I want the orange cat, and the orange cat I am going to use is a very popular orange cat, and that's sodium ethoxide, NaOET. ET standing for ethyl, O obviously for oxygen. Let me draw you the product, and then let me discuss a little bit about what's happening here. So the product is going to be this. Just replace the gray cat, which is the bromine, with the orange cat, which is the OET, in the bed. So the cat bed is this alkyl group. Okay, so we did a substitution just like we did, or just like we see in this picture here. Now, I'm not telling you what the process is, because all I drew was the starting material and the final products. I didn't show you any of the intermediates or any of the transition states for this reaction. That will come later, not even in this video, most likely. Okay. Now, the thing about this chapter is that you need to be able to interpret the type of molecules you have, and we know this as an alkyl halide. Okay. But the reagent also is super important for us to recognize. Okay. This NaOET you have to visualize this as a salt that gets separated in solution. And we have Na plus OET. ET stands for ethyl, and if you want to draw the line structure, it's just like that. But even more importantly, or just as important, is that this oxygen is negative. So you know that a salt, in a lot of cases, it's a positive ion and a negative ion. So whenever you see sodium ethoxide, potassium ethoxide, lithium ethoxide, you have your counter ion, positive cation, and you have your anion. The name of this is ethoxide, like ethyl oxide. And this is going to act like a nucleophile. What is a nucleophile? A nucleophile is a molecule or atom that's electron-rich. So that's the abbreviation for electron and rich. Okay. It's also, you can think of it as the attacker, and I'll show you that in just a bit. Okay. Or you could think of it as what? A lover of nucleuses. So nuclei are positively charged. Now it could be a full positive or it could be a partial positive. So I know that I have a nucleophile. Where's the electrophile? The opposite, electron loving. So here's bromine. From the periodic table we know it's electronegative. And as it pulls electrons away from this carbon actually builds up a partial positive charge. So there's your complement. Those are your opposites attract. Okay. And as this comes in, it's going to kick out the bromine. So let me show you the mechanism for this one. Again, the main point is that this molecule, the anion, is acting like an attacker. It's acting like what's called the nucleophile. In contrast, this molecule, the one that's being attacked, is the electrophile. Okay. Let me show you the mechanism to get this product here. You notice that the sodium is not anywhere here. Where is the sodium? The sodium maybe is pairing up with the bromide. Okay, because we did get rid of this bromine, but we substituted it out. The mechanism is pretty straightforward, actually. The thing about this unit is that we're going to look at many more details, not just the product, but stereochemistry, regiochemistry, kinetics, how fast the reaction happens, etc. But let me show you the mechanism. It's actually just one step. Okay, I'll use pink. Opposite attract. The negative is attracted to the positive, partial positive, okay, which forces out the gray cat. You notice that for the mechanism, I already separated out the sodium. I got rid of it. That's why it's going to be very important that you practice recognizing what is the nucleophile. It's not this whole thing, sodium ethoxide. It's not sodium, it's just ethoxide. This molecule here. If you think about what's happening, the dot is carbon is being attacked by the ethoxide and kicks out the bromine. And if you want, normally I ask students to draw out every single product of each step. So we did kick out a bromine. Look at this reaction. Orange cat, gray cat, cat bed. Is this reaction following the row 1 cartoon or the row 2 cartoon? the ethoxide comes in and attacks, kicks out the leaving group. It looks like it's the second row. Okay, looks like the second row. You know, in the first row, the leaving group leaves without any help. Okay, but here, it looks like the leaving group left was forced out. It had help from the orange cap. Okay, I'm not going to tell you what this mechanism is called. It is definitely substitution. Okay, but it's a special type of substitution that we won't get to in this video. Okay, it's a substitution. You want to recognize substitutions because the halide left and you replaced it with something else. That's how you're going to recognize a substitution. Now, this is a little bit tricky because in Unit 7, most textbooks have another type of reaction in Unit 7 called elimination. And textbooks tend to cram both substitution reactions and alkyl halide elimination reactions. Okay. Those of you who are familiar with that concept, like maybe you're retaking Organic 2 or Organic 1, or maybe you read ahead, because most textbooks combine my Unit 7 and my Unit 8 together. So let me show you what other type of reaction can happen. It's called elimination. We have this alkyl halide. Okay. Same alkyl halide, same gray cat, same bed. And honestly, we have the same partner. But I'm going to pretend something different. I'm not going to pretend that this is a nucleophile. I'm not going to pretend that this is an attacker like I did up here. Okay. This molecule has dual personality. How about what if it acts like a base? What a base does, it grabs a proton, right? Like in acid-base reactions. Let me use green. We're going to go over this more specifically in Unit 8. I just want to introduce the idea that we have two of the same starting material, but we could have two different products. Okay. What's going to happen here, I'll use green. I'm going to grab the hydrogen that's next to this carbon with the bromine. I should label these. This is considered the alpha carbon, the carbon that's attached to the halide, and I want to find some space. This is the beta carbon right here. This is called beta hydrogen elimination. Don't worry about that just yet. So this bond collapses. I'll go underneath like this. Okay. So now you notice that this carbon has a double bond, a bond to bromine, a bond to carbon, and a bond to hydrogen. It has too many bonds. So this is going to be forced out. Okay, if you could follow my mechanism arrows telling you exactly what to do, it looks like you're making a bond to this ethoxide. Okay, so we could draw that. Okay. But for the 4-carbon chain, this carbon right here only has one hydrogen, and a double bond was made. There's a double bond. Bromine got kicked out. This carbon over here is still good. It has one hydrogen, so it's neutral. That's your product. This is called elimination. Okay. Look at the two reactions that are on the screen right now. Same starting material, but one is acting like the nucleophile. The same molecule also can act like a base, and we get two different products. If you want, circle the main organic product. That one and this one. I'm not saying that it's the major product, although it is. I'm saying it's the product, it's the carbons coming from the main starting material. And hopefully it's obvious that we're really worried about these 4 carbons. Okay, and this ethoxide is just a reagent to cause a reaction on these 4 carbons. This is a substitution product. This is the elimination product. And it's going to be an alkene. Most cases. Okay. Do you see that? It's going to be the alkene. Zoom out. Okay. For this unit 7, okay, we're only going to focus on substitution. This elimination, I'll put a note here, this is unit 8. Okay. I split it up because both of them are pretty large sections of the textbook. Because with substitution, we are going to learn those 2 methods, right? Because we have these 2 cartoons. And right now we've seen the mechanism for the second cartoon, the second row. Okay. The other thing is that I have, I don't know, to me it seems like infinite number of different molecules that I could substitute onto this molecule. I could have used a nitrogen anion. I could have used a sulfur anion. I could have used, instead of an alpha group, I could have used a methyl group. I could have used an isopropyl group. The thing is, you shouldn't let that overwhelm you because it's doing essentially the same thing. Okay, you're essentially just replacing the bromine with whatever you are using as a nucleophile. Okay. Let me just make sure that I'm not missing anything super important. Okay. Let me go through. I mentioned the infinite number of nucleophiles. It's not infinite, but there are a lot. And if you let it overwhelm you, or if you don't understand how these nucleophiles work, then it will get overwhelming. Let me show you a couple of nucleophiles. And also, let me get a new bed and new gray cat. So, for instance, I'll make it super simple, very tiny. H3C, and I'll use a chlorine. Okay. So in this case, we are going to attack the nucleophile with its lone pair. It could be anionic or it could be neutral. We're going to attack this carbon and we're going to kick out this chlorine. But what kind of nucleophiles can I have? The first nucleophile I can have is just an OH minus. Okay, but again, you have to recognize that the reagent, I could buy it from a chemical company and they will sell me sodium hydroxide, NaOH, or lithium hydroxide. It is your responsibility to remove the counterion, remove the cation, and recognize that this is your orange cat. This is your orange cat. So when we do the reaction with your alkyl halide, simply you get substitution at that position. The OH minus replaces the chlorine by attacking this carbon. You made an alcohol. Next, we already saw this example, but an oxide. Okay, I'm not going to draw the lone pairs because I'm not drawing the mechanism. If I were to draw the mechanism, I would want to draw all the lone pairs on that atom that's attacking. Okay, so this one, I'm not sure how strong your classes of molecule naming is, but when that methoxide comes in and attacks that carbon, you have this. Okay. But that's the same as what? That's the same as that, right? An oxygen with 2 methyl groups, 1 on each side. That's called an ether. Ether. Okay, a couple more, a few more. Do you see a pattern? Once you separate the counterion, the cation, right now we have anionic nucleophiles. Anionic nucleophiles. And here we have H3C, SH. Okay. Or if you just want to use line drawing, it's such a small molecule, I think it looks a little strange to use line drawing, but everyone should know that there's a carbon right there. Okay. That's called a thiol. For my class, probably I have not talked about the functional group SH or the molecule thiol, but whenever you have a sulfur and an H, that's a thiol. What else? Let me show you this one. This one's an interesting nucleophile. Potassium cyanide. This is interesting because if you remember your general chemistry, you know that Cn is actually a polyatomic ion, an anion actually, and you could break it up into K plus, Cn minus, and actually you should know that Cn minus is this, right, a triple bond. That's your nucleophile. So envision this molecule attacking the carbon and kicking out chlorine. And if that's the case, we get, what do we get? We get, you could draw it like this. That's perfectly fine. Or you could draw it like this, which is a little bit stranger, but, well, I shouldn't say stranger, but it's less common to draw it out like that. It's the same thing. Okay. This is called a nitrile. Class of molecules that I know my class, I didn't teach my class yet. Okay. It doesn't matter really that you know the class of molecules. What matters is, could you, based on the nucleophile, figure out what your final product will be? Now, maybe one more. Okay, yeah, one more. And this one's pretty interesting. Let's take sodium N3. This is called azide. Azide. It's interesting because, what is this? Obviously you have an Na+, but the 3 nitrogens is something unusual. N, N, N. Okay. Give me 1 second. Let me make sure I'm doing this correctly. Yes. I was checking to make sure that all nitrogens fit the octet rule. 2, 3, 4, 5, 6, 7, 8, good. 5 minus 1, 2, 3, 4, 5, 6, isn't it? Okay, so this is going to look a little strange, but if you do the formal charge equation, your N3 group is that. I know it looks unreasonable that you have so many charges, but this is doable. At least we don't have charge repulsion. Okay, that would be very bad if there were 2 pluses next to each other. So what is this? You could simply draw the molecule like that. Okay, or you can draw it out. I would not draw it out actually, but we could double check if it's neutral. Right, this is positive, and this is still negative. This middle nitrogen, or this nitrogen on the left, is neutral now. Think about it. When this lone pair attacks, this nitrogen will obtain a 3rd bond. Nitrogen with 3 bonds and 1 lone pair is neutral. Okay. These are all not all, but these are all anionic. There are many more nucleophiles that we can use. Okay. Like I said, we could change this methyl into an ethyl, into a propyl, etc. but these are the common ones. Cyanide, maybe I didn't write that yet. The cyanide attacks to make a nitrile. I want to go over neutral, which is a little bit more difficult. Let me redraw my cat bed. Let me draw my gray cat that's leaving. Okay. And plus. Okay. Neutral is a little bit trickier because you could still have substitution, but look what happens to my molecule. Okay. Do you notice that if the water attacks, it's bringing in 2 hydrogens, but it leaves off a hydrogen, the second hydrogen is removed. Because if the second hydrogen was there, it'd be positive. So normally you don't want positive molecules because they're a little bit less stable, especially if they don't have resonance. The initial product would have been this. That. But this is an intermediate. Okay. And then in the last step of the mechanism, you remove the hydrogen to become neutral. So you do want, if you can, neutral molecules. There's one other example where we have, actually 2 examples, where we could have the same idea. And what if we do this? Okay. You're doing a substitution. So if you're panicky about, a bunch of different nucleophiles, find your alkyl halide that's going to be attacked. And then so your attacker has to be the other molecule. To attack something, what do you need? To attack something, you need a lone pair. So find a lone pair. The lone pairs are on this oxygen. That's why when I make the connection is not to any of these 3 carbons. The connection is to the lone pair which attacked this carbon up here. So the point of attachment has to be that oxygen. And then that oxygen has 3 carbons. The thing is, initially that hydrogen was right there to make the oxygen positive. But again, like up here, we get rid of that hydrogen to make it neutral. So this is another ether. It's just an ether made from the neutral alcohol. But over here, see, we didn't use alcohol, we used the, they call it an alkoxide. It's an alcohol without the hydrogen. See, you make an ether up here, same thing. We made an ether down here, except now our nucleophile was neutral. Let me give you one more neutral nucleophile. Okay. Identify the lone pair, or draw all the lone pairs, and one of them is going to be the attacker. Can you draw me the product in this case? Remember, you want to neutralize it. So if your nitrogen has 4 bonds, it will be positive. We don't want it to be positive. Okay. Alright, the answer, you could draw it like that. Okay. Again, initially it had 3 hydrogens, but we had to get rid of it to make it neutral. Good. So I think what's going to happen here is in the next video we'll go over a couple more examples. Okay. And we'll make it look like a test problem, a fill in the product test problem. And then we do have to go through all the subtleties like kinetics, stereochemistry, I think there's regioselectivity as well. Okay, solvent effects. All of this is within substitution. We are not going to consider elimination until we finish substitution and we go on to the next unit. Okay, so all of these videos in this unit are just based on just the substitution reaction, even though in some cases elimination can happen. So that's my disclaimer.